All right. Awesome, my remote control. Oh, there it is.
Oh yeah, we're going to work before. Let's go.
Okay, so we need to finish up some things here. So we know in osmosis or in diffusion, molecules are going to move on their own from a high to a low concentration. Okay? In osmosis, we're specifically talking about water moving through a membrane from high to low concentration. So have we talked about it if you're dehydrated and you go to the hospital? Have we talked about that before?
No.
So if you have become dehydrated, severely dehydrated, like you're sometimes like running the Boilermaker, people are always pass out on the side of the road, they have to be taken to the medical tent, often because they're dehydrated. And the treatment for that, if their person's unconscious, they can't give them glasses of water to drink. So they generally will give them an IV. They hook them up to an IV. IV stands for what? Intravenous. It means a needle that's going directly into a vein. And they will give a person IV fluids to bring up their hydration level back to normal amounts. But when they do that, in the IV bag, they do not just put pure water. Okay? And the reason is because of osmosis. Can you think about why they wouldn't give somebody pure water in their IV into their bloodstream? Jonathan?
It would be able to fuse into the blood cells because it's small enough to move through the semi-permeable membrane.
Yeah. So because of osmosis, we'll talk about it in a minute. So they give them, what do they give them instead? Do you know what they get? They don't get pure water. I don't know what they get. No, that would be a pain reliever. Who wears contacts? Anybody?
No,
What? Yeah, it's a solution. It's specifically a saline solution. It's a mixture. It's a balanced solution of water and various salts that's balanced properly to have equal concentration of water as your blood cells. So here, that would be this situation. So here we have some blood cells, obviously bigger than they normally would be, in a solution. And they basically remain the same size. This is what it would look like if those cells were placed in a solution where there were equal concentration of water inside the cell and in the solution. If there's equal concentrations, basically water moves back and forth equally. So they're not going to gain water, they're not going to lose water. In diagram B, the blood cells have been placed in a solution that has a lower concentration of water. And what has happened to these cells? We talked about it in our question of the day. Bianca?
They shrivel up.
They shrivel up. They lost water. They lost water because water went from a higher concentration in the blood cell to a lower concentration in the solution. This scenario explains lots of different things. Like after you eat a bunch of salty potato chips, you're thirsty because the cells in your cheeks and your mouth, they lost water to that salt in the potato chips and so forth because of osmosis. Okay? If you put salt on a slug, they die. They die because they dehydrate due to losing water by osmosis. If you're stranded on a boat in the sea and you're dying of thirst, should you drink seawater? No, because you will dehydrate more quickly because of osmosis. If you think about it, your cells are already dehydrated because you've lost a lot of water. If you drink seawater, which has a lower concentration of water than your cells, water is going to leave your cells, and you're going to dehydrate even quicker. Okay? Possible, you're going to die of dehydration first. So all of those things can be explained by osmosis. Okay?
What would you do?
You have to get pure water, fresh water.
How?
Well, at the end of class, I'll explain how if we have time. All right, and C then. Look at situation C. What has happened there? Joey?
It's a high concentration.
Yeah, these cells have been put in pure water. And is pure water of a high concentration of water? Yeah, it's 100% water. Higher than the blood cells. So in this case, what Jonathan was saying, water goes into the blood cells, causing them to enlarge, possibly causing them to burst. It's called hemolysis. And they don't give people pure water in their IV because this would happen. Their blood cells would expand and they could burst. Okay? So they give them that balanced solution. Your contacts, you don't put them in tap water from the sink because then water would go into your contact lenses through osmosis and the shape would be altered. So instead you put that solution, saline solution, that's balanced with your contacts, and therefore they basically stay the same shape. So this is key to know, is that when cells are put in a lower concentration water, they lose water and dehydrate and get smaller. If they're put in a higher concentration water, they get larger. They expand, they could burst. All right, now how quickly molecules diffuse is a factor of heat energy as one thing. Heat energy, as we heat up molecules, they move more quickly. And if the molecules are moving more quickly, what do you think about the rate of diffusion or osmosis? Think it also speeds up? Yeah. It does. Those molecules are moving faster, the molecules diffuse faster. So we can increase the rate of diffusion by adding heat. Another factor that will determine how quickly diffusion takes place is the surface area that's available for those molecules to move through. And this becomes important when we talk about some human anatomy, physiology. We'll talk about that in a minute. If we look at these two jars of water, which a dye was added to, at the same time, which one do you think was warm water and which was cold water? Eli?
With the light, the warm one.
This one?
Yeah.
No. It's this one. Because what's happened more quickly in this one?
It's spread.
Yeah, the dye has diffused more quickly. Here it's still sort of, you see it on the bottom there. It hasn't diffused as quickly. Because it's colder water, the molecules are moving slower. Surface area becomes important when we talk about our bodies. Our intestine is adapted to absorb nutrients from our foods, and it does that through diffusion. When you eat a bunch of sugar, for example, there's a high concentration of glucose moving through your intestine in that food. There's a lower concentration in your blood, and so glucose diffuses into your blood through your intestine. Now, if your intestine, it's not like a hollow tube that's nice and smooth on the inside. It's not like a hose. The inside of your intestine actually has millions of these villi, they're called, these ridges and bumps. Sort of, they look like fingers poking up from the intestine. And all of these ridges increase the surface area for molecules to move into your bloodstream. In fact, if your intestine were just a smooth tube, it'd have a surface area of about your desk, about 1.5 square meters.
Oh.
But it doesn't. With all these bumps and ridges, the actual surface area is about 2 full basketball courts, 250 square meters. So that is a vast surface area for nutrients to diffuse into your blood. The same is true in your lungs. Your lungs, each lung is not like a hollow balloon on the inside, nice and smooth. They're made of these little clusters of air sacs called alveoli. They look like little broccoli florets. And so each of those little air sacs increases the surface area of your lungs. Surface area of lungs is about a full basketball court. So that's all surface area where oxygen can diffuse into our blood. So our bodies rely on this principle of greater surface area, greater diffusion. Now, what we've been talking about thus far, diffusion and osmosis, these are types of what we call passive transport. Passive transport is when molecules move, but it doesn't require any energy. It just happens. So when molecules are moving from high to low concentration through osmosis and diffusion, that's passive transport. I didn't have to add any energy to make the molecules diffuse into the egg, right? When we did the egg or the gummy bear. That just happened on its own. And it happened because the molecules are moving from high to low concentration. Now, it is possible for molecules to move the opposite way, from low to high concentration. It has to happen in the human body, in cells, all the time. But it doesn't happen on its own. Those molecules have to be forced to go the opposite way, and that's what active transport is. The cell needs to use up some energy, forcing those molecules to go the opposite way. One example in the cell that's very common is the proton pump, which pumps hydrogen ions from inside the cell to outside the cell. But it does that against from low to high concentration. It takes some energy to do that. If you remember my example, remember when I said I was going to put all the 7th graders in this room?
Yeah.
When I opened the door, would I have to push people into that room, or would they just go on their own? Yeah, they just go on their own. They don't need me to exert any energy. But if I had all the 7th graders in the school in this room, and then I wanted a 9th grader to come in here. There's no 9th graders. But I could grab a 9th grader. They're not going to come in here on their own, but I could grab them and force them into this room. Right? I would have to exert a small amount of energy actually doing it. They'd be moving from a low concentration to a high concentration, but I could do it. I just have to exert some energy. Right? So that would be an example of active transport, right? Moving molecules the opposite way.
So it's kind of like calories, how we have to, like, how we get calories and how we burn them out by exercising.
We use those calories to get energy, but I would say not really that close. All right, just to review here. If we have some dialysis tubing filled with 98% water, 2% salt, what happens if we put it in pure 100% water? Raise your hand if you can tell me what would happen there. Nicholas? It'll get bigger. Water is going to go from 100% water into the 98%. Water will always move toward the lower concentration. It's going to expand or enlarge. What if we put it in beaker B, which is 90% water? What's going to happen, Herschel?
It'll get like smaller.
It's going to get small. It's going to lose water. Water is going to leave the bag and go into the beaker. It's going to get smaller. In the last situation, what happens if I put it in a balanced solution? Kristen?
It's gonna stay the same.
It's going to stay the same. Water will move back and forth, but with equal amounts. It's not going to change in size. Any questions about that? All right, let's come back to here. Yeah, Eli, a question?
Yeah, why would it get smaller in beaker B?
Because look at, so we have 98% water in the bag, 90% in the beaker. So water is going to go toward the lower concentration.